All right, well, we're going to take on, just remember what we're trying to do. You have A of n is equal to negative A of n minus 1 minus A of n minus 2. This is the recursive formula, and we're trying to find the closed form solution, not by trial and error. That's the goal. And we know that A of n is going to take on three different forms. It's either going to be C1 lambda 1 to the n plus C2 lambda 2 to the n if you have two solvable. In other words, you have two, you can factor it out and you get two different lambdas, like 2 to the n and 3 to the n. But you also have this same form if you have the complex. It's just going to look different, okay? And the way it looks different is we're going to skip some things like finding C1 and C2. Well, we're not going to skip it, but it's going to have a little bit of different look to it. The other form, and you might have to help me with this one, is it C1 plus NC2 times lambda to the n? Does that sound right for the two duplicates? I think that's right. And that's if you have a double root. So this is double root. And this is 2 roots. And this is non-complex. But it's also complex too. But the complex method's going to be a little different. So here's what we're going to do. We're going to get to that point. So you get the idea of what we're trying to do. Those are the three that we have. We put everything here. We're going to let lambda equal to A of n minus 1. So A of n is going to be lambda squared. A of n minus 1 is going to be lambda. And A of n minus 2 is just going to be 1. So here's set equal to 0. Lambda squared plus lambda plus 1 equals 0. Got your A, B, and C's. And you're going to go lambda is going to be equal to minus 1 plus or minus square root 1 minus 4 times 1 all over 2 times 1, which is going to be negative 1 plus or minus square root of negative 3 over 2, which actually is something that we can recognize. This is negative 1/2 plus or minus square root of 3 over 2i. We got this far yesterday. Let's graph it on the complex plane. Here is negative 1. Here is negative I. Here's I. Now look at what happens when you go back negative 1/2 up square root of 3 over 2. You're about right here. This angle you're going to recognize, and you look at the point, negative 1/2 square root of 3 over 2. Do you recognize that arc length? 2 pi over 3. Yep. And then this one, the other one, is just down here, negative 1/2 negative square root of 3 over 2. And of course, there's an I on here, makes it in the complex plane, but it's still negative 2 pi over 3. Tell me about the C values if this, if you go, let's do it this way. If you look at this arc length and this arc length, what can you tell me about the C's? These two C values. They're the same. Yeah. So since C1 equals C2, it's going to make our calculation a lot easier. And this is what I didn't have yesterday for you that's going to make a lot of sense. So I've got all of this so far. I'm going to shrink it. Great. And then we're going to take this piece here, A0 is equal to C1 lambda. It's going to be nasty, isn't it? But look at this. It's going to be lambda to the 0 plus C2 lambda to the 0, right? So lambda 1 to the 0, lambda 2 to the 0. What happens is if A0 is 4, C1 times 1 plus C2, and if C1 is equal to C2, what is that going to be equal to in this example? They're just going to be 2. And you can always bet on that for the complex. If you have an A0, it's just going to be C1 and C2 are going to be half of this A0. So if you want to, C1 equals C2 equals A0 over 2. If that's a formula you want to put in your back pocket for complex, you can do that. Mm-hmm. So that's the easy, fun part. But we still don't have an equation yet. And the reason we don't have an equation is because now we have A of n is equal to 2 lambda 1, which is negative 1/2 plus square root of 3 over 2I to the n plus 2 times negative 1/2 plus minus square root of 3 over 2 I to the n, right? That's what we have so far. And do you like that answer? No, you don't like it. I don't like it either. So look what we can do. Back in HL2 times and honors pre-calc times, we had this R and we had X and we had Y times I. And one of the things that we did is we said X is equal to the cosine of theta times R, and yi is equal to R times the sine of theta times I. Does that sound familiar? Oh, yeah, but it makes sense. So let's do this even easier. Let's do it this way. Let's just call this cosine of theta, sine of theta. And if this is 1, this is what we're used to. If we multiply everything by r, this is what that's going to be used to. So a point up here was called x comma y, and in the complex form, we can write it as x. We don't use it as a point. We write it as x plus yi. And that's the complex form. Oh, can't remember what letter we called it. It's not R. It's, can't remember. But anyway, that's the form. So then whenever we write this x, it's going to be r cosine theta plus I r sine theta. And take out the r, you get cosine theta plus I sine theta. Well, times r. Shortcut for this is called cis form, theta. So that's just going to be r cis theta. We ready to use this then? Okay. So making a triangle here, we have theta, and this was negative 1/2. This was square root of 3 over 2. we need to find what r is. So what's 1/2 squared plus root of 3 over 2 squared? What's 1/4 plus 3/4? 1. So r cis theta is going to be equal to 1 cis. This one is going to be 1 cis 2 pi over 3 to the n. And this one's going to be 1 cis negative 2 pi over 3 to the n. What do you think? Yeah. All right. Now, we unfortunately are not done yet. What we have here is 2 cis 2 pi over 3 to the nth power. And with cis, there's a property, it's a log type property that's like logs. What can you do with the power if you have a function to a power in a log? What can you do with the power? You can do the same thing with cis. So this becomes 2 pi n over 3. And this becomes cis of negative 2 pi n over 3. Do you like this? Okay. So now that's de Moivre's theorem, and I'm just going to throw that in there. De Moivre's theorem. And you folks remember that probably. Cis theta to the n is equal to cis n theta. It's just a little property that we proved back in HL2. Not done yet. Now, what we're going to do is we're going to expand this. Remember what cis meant. It's the cosine of theta plus I times the sine of theta. So this is going to be, in purple, 2 cosine 2 pi n over 3 plus I sine 2 pi n over 3. This is times 2. Okay. This one's going to be plus 2 cosine negative 2 pi n over 3 plus 2I sine negative 2 pi n over 3. So we have, again, 2 cosine 2 pi n over 3 plus 2I sine 2 pi n over 3. Now I have to remember my properties. For cosine, what was the cosine of negative theta equal to? Cosine of theta. So this is 2 cosine 2 pi n over 3. Property, cosine negative theta equals cosine theta. We do it this way. If you take your arms like this, go up theta, down theta, what do you notice about the cosines? What do you notice about the sines? Opposite. So this is going to be minus 2I sine 2 pi n over 3. And that's because of the other identity. Sine of negative theta is the opposite of the sine of theta. Then I notice something here. What do I notice, Musa? Those are gone. And so we'll have 4 cosine 2 pi n over 3 is what A of n is. Yeah. It's long. But let's think this through here. This is A of n. This is essentially A0, this is the cosine of theta times n, isn't it? A little general case for you. All you really need to know is what theta is, Na0, and you can check it. So there you go. That's the problem that we worked on yesterday, all worked out. If you run into any of those, and I think you do, I would guess with problem 2 you'll run into that. See if you're able to figure out with the Fibonacci sequence what that's going to be.